Today we'll continue we're essentially on chapter 4 of CLRS. So if anybody is wondering, and if you'd like to read up on the book, I'm not covering all the chapters in complete depth. So you just have to look at my topics, and hopefully, if you just take a look at the table of contents of CLRS, should be able to figure out what topics we've covered and what we haven't. But if somebody is really curious, then I can try to post that as well. Do let me know. So we're on the general topic of divide and conquer algorithms. And we're looking at how one can actually design an algorithm such that it is converted into a divide and conquer algorithm. And we saw an example of sorting. And you've seen, presumably, a lot of techniques for sorting. And not all of them are merge and sort, okay? Or not all of them are divide and conquer. So merge sort is one of those examples. There are other examples as well which have the same philosophy of divide and conquer. And so in the last lecture, we were looking at the proof of correctness of merge sort. And that's where we stopped. So let's continue on from that point. Okay, so not using poll everywhere that much anymore, so but you can still take a look at that. All right, so just a few slides, and just a reminder, I do use the following notation to indicate that a particular slide is a previous revision slide, and it's generally just there for reference. And so we looked at an example of linear search. Not sure why this is continuously popping up. Okay. And we looked at how merge sort would work if you give it some sample numbers. And we looked at 2 pseudocodes, one for the main merge sort, and then for the merge function, which actually does the actual merging of 2 subarrays. It converts them into a single array, which is finally sorted. So essentially, this is where we stopped. And we had a brief discussion in the last lecture as to what would be a loop invariant. And so if people, and there was several suggestions as to what would be the loop invariant. Can somebody remind us where we were? Some of you had some interesting suggestions. Yes, please. Yeah, that was one of the responses. I don't know if I gave a good response to that. It wasn't the best suggestion, but yes, go ahead. Let me just stop you. Let me again say, the reason why that wasn't a great suggestion is because that is already given. So if you go back, you're already given the subarrays which are already sorted. Okay, so that's not a good loop invariant to, basically trying to figure out, can we come up with a loop invariant which at the end, at termination, would tell us that this final array is sorted. Okay, so just the fact that the 2 subarrays are already sorted is not going to help us figuring out how the final array is essentially sorted. So we have to, but I'll go to the gentleman who just had the other suggestion. Yes, I'm sorry to interrupt you. Yeah. Yeah, so we had N1 and N2 being the size of the subarrays, but the indices are I and J and K, okay? So if you remember, this was a loop that we were focusing on, that we wanted to say, well, we need to have a loop invariant for this particular loop. So in this particular loop, the indices, the variables are K, I, and J. So we need to say something in terms of K, I, and J, which would help. So just continue on with that thought. Yeah. A1 through K is sorted. Okay. And yeah, just keep going. Okay. All right. So K minus 1. All right. So let's say I and J are somewhere in the middle. And what you're saying is that Li is greater than equal to what? A at K minus 1. Okay. And similarly for Lj. Okay, let's just try to examine that suggestion. And your name again is? David? Okay, so let's examine the suggestion from David. He's suggesting that A1 through K minus 1 is sorted, right? So that seems to be pretty reasonable suggestion, because essentially as you're going from P to R, and right now you're in the loop where K is equal to K, all right? So what you're saying is that you've already sorted everything before up to K minus 1. Great. So that would say that as we go up to R and we end the loop at R plus 1, it would immediately tell us that, very useful suggestion at the termination point that the whole array A is sorted. Okay, if we can prove that, that's great. Now let's examine the other parts. The second part of your suggestion is that Li is greater than AK minus 1. Okay, so let's just try to examine that. So let's say we do the first round and we look at Li and Rj and we look at these two values and we say, well, which one is smaller? So clearly it's going to be the second part because Li is not smaller. Well, yeah, Rj is smaller than L of I, right? So we're going to go through this part of the loop and we're going to copy this chap over here, all right? And we're going to copy the first element of the Rth array into the first element of the A array, okay? And then we're going to increment J, okay? And J is now going to be equal to 2, all right? So what you're saying is that, let's look at your second suggestion, which was Lj is going to be greater than or equal to AK minus 1. That is in fact true. Okay, so great. Any other thoughts? Any other suggestions? Any modifications or complete different opinion? Yeah. You'll have to speak up. I'm sorry. Are not what? From where till where? Okay, from I till the end. Okay, so what you're saying is that instead of this and Jane, is it? Okay, so Jane's suggestion is that you go from everything from Li on to N1 plus 1 perhaps, because we do have infinity over here. That has not been placed in the A array. Okay, so let's examine that thought. Well, for Lj, that would be now J is equal to 2. All right, we've just copied R1 over here, and essentially what Jane is saying is that everything from this point onwards has not been placed into array A. Okay, which means that everything before that has been placed. Okay. So two reasonable suggestions. Any thoughts, any further thoughts? Do people agree with David, or was it David? Sorry. Yeah, David or Jane more? Any thoughts on that? Should we have vote? Anyway, so let's take a look at the actual loop invariant. All right, so here we say that, and it's actually pretty much in line with what Jane is suggesting, which is, and a combination of what Jane and David suggested, is that the subarray AP through K minus 1. So we have P starting from here. All right, so P is the starting point, R is the ending point of the array. Everything from P to K minus 1. So if let's say K is equal to 2, then everything in this range contains the K minus Pth smallest elements of L and R in sorted order. Okay, so essentially that's more or less what you're saying is everything in this range is sorted, and it contains how many elements. That's kind of obvious because it's just the element counting. That's K minus, that comes out to be K minus P. Okay. And the second part is that Li and Rj are the smallest elements of L and R that have not been copied into A. Okay. So a slight difference from what Jane said. And here we also saying that not only have they not been copied, but we're also saying that they are the smallest elements of L and R. Okay. So in other words, we're not saying that, we're over here. So let's say J could be over here. Okay. And we somehow skipped this chapter. And we're saying that these guys have not been copied. Okay. But we're not necessarily saying that these have been copied. I'm kind of saying that. But is this part really important, that they're the smallest elements of LNR? Is that really necessary to be stated? And Jane, can you make a case for that? That seems to be redundant information, loop invariant, or somebody else? Yeah. I'm sorry, can I get your name again? Sorry? Harrison? Okay. Yeah. Sorry, say that to the last part again. Must be the smallest element, yeah. Yeah, it could be sort of a sub, statement. We sort of based on the other facts. It can be proven that that those are the L sub I and R sub J elements are in fact the smallest elements which have not yet been copied. But it's nice to sometimes just express that if it really becomes helpful. Yeah. Okay, so interesting suggestion. And your name again, sorry? Sorry? Levi. Okay, so Levi is suggesting that do we really have to state this stuff? Okay, basically I think that's what you're saying, is that isn't this sufficient? That sorry, the first part, isn't that sufficient? Why do we need to have the second part? If at the end of we're going from K is equal to P to R, by the time we get to K is equal to R, if the first statement says that it contains the subarray from P to K minus 1 contains the smallest elements of L and R in sorted order, that's essentially it should be sufficient, right? So any thoughts on that? Why do we actually need to have the second statement? That's a good. Well, okay, so then I have a problem, because you're saying that we could have the second statement and not have the first statement. There's no reference to the
part of the algorithm handle creating coordinated is contained within 12.
Okay.
But the actual is sort of let's say would not be and basically this will be saying a lot.
By line 11, you're talking about this particular line, and if you could state that as a loop invariant, and so because see the line 11, all it's saying is that K is going from P to R, and that's only going to say that this loop is going to terminate, right? That's all, and presuming that K is not being changed internally, that loop should terminate, right? But that's just the termination condition, right? So a loop invariant doesn't necessarily just have to show that the loop is going to terminate. Remember, if you go back to our loop invariant, it has to, first of all, have to have an initialization. Well, it has to, at the termination stage, you must say something interesting that can go ahead and actually prove. So that part is very important in the loop invariant. It has to say something interesting when it terminates. Yeah. So it has to say something which can be used to prove, the accuracy of the algorithm. So just the fact that it terminates is not going to be good enough. Okay. So yeah. So let's go back to the thought. I think so I think we had that discussion that it seems reasonably clear that this particular part, the smallest element of L and R, that those are in fact the smallest elements, may not necessarily need to be stated, but if you do state that, it comes out handy as you go forward. Okay, because now we have to actually prove this. Okay, so just stating the loop invariant is maybe 20% of 30% of the job. The bulk of the proof, the bulk of the issue is now to be able to prove that. Okay, so now we need to be able to prove that in 3 stages, right? So initialization, maintenance, and termination. Okay, yeah. So what you're saying is that we need the second part to be able to confirm that there are some parts of the remainder of L and R which have or have not been added to A. That have not been. Yeah, so if you completely remove this part, we're not saying that you completely do away with that second part. It's just saying that are those the smallest elements? Okay, we were just having a small debate on that. Now, do we really need to say, we could have just said the L and R are that have not been copied, which is what Jane suggested, right? She just suggested that those have not been copied. She didn't say that they're the smallest. Okay, so that was just that debate. Okay, but your point being that you could have some elements, so I'm not sure if I completely understand your point, but okay, yeah, so that is the issue. You see, we are already given that L and R are already sorted. So that precludes that possibility. You understand? Sort of precludes that. It would require a bit more discussion to be able to completely exclude that. But let's go on with this thought that we're going to say that they're the smallest elements and that that have not been copied. Okay, let's go ahead with that part. Okay. So now let's see if we can somebody tell me, can you prove the initialization that before the first iteration, the loop invariant is in fact true? Can somebody prove that? State it out. Kind of the most simplest part is the initialization because it's kind of trivial. Yeah, go ahead, please. Yeah. Yes. Yeah, yeah. I'm sorry. Can I get your name? Sorry. That's a hard one for me. But I'll just go ahead with that. So you'll have to spell it out for me sometimes. I can't hear all the consonants sometimes. So what's been suggested is that well, clearly A from P to K minus 1 and K is P. Okay, so going from P to P minus 1, that array doesn't exist. All right. So clearly, you know, so that part and K minus P is 0. Okay, so K is equal to P, so K minus P is 0. So that's sort of trivially true. Okay, the first part. And the second part, as you suggested, is that L1 and R1 are just the first numbers, and they presumably, because the fact that they're already, the L and R are already sorted, so they are clearly the smallest values of L and R, and they have not been copied yet. Okay, so sort of the initialization is trivially true. Okay, agreed. And that's what we have over here. We've just stated that, so you can read this up. Okay. Now let's take a look at the maintenance. So this is, generally speaking, the most difficult part of a loop invariant, is to figure out the maintenance. And a lot of times you can sort of hand wave through it, because if you know that it's true, you can sort of say something very simply, and you let the professor figure out whether what you've said is in fact complete and accurate. And PAs and LAs and professors don't like that. So you need to be a little bit more thorough in terms of stating the maintenance to be able to prove the maintenance. Okay. So if you remember this particular slide, when we looked at the linear search, I had suggested sort of a trick. It's not really a trick. It's just a way of doing that. Is that I'm assigning another variable. Okay, so I'm saying I'm assigning a temporary variable I is equal to K, which is the value of I in the previous iteration, to differentiate the value of I in the current iteration. Okay, it's just something that helps. Okay, so can you suggest, let's say, to start off with, if you want to do the maintenance, how would you suggest, and going with my philosophy, how would you suggest what temporary variables would you like to assign? What could they possibly be, and to which variables will we assign the temporary variables? So how many of them are there in this particular loop? The 3, yeah. So let's say you have I, and you assign it, sorry, you have K, and you have I and J, okay? So, so let's assign those to K1, and this is the previous loop, and I1 and I2, okay? So these are the values of Ki and, sorry, so that's J1, okay? So those are the temporary variables assigned to Ki and J for the previous loop. And in the current loop, what would be the values? Current values, kind of trivial question. Yeah, K1 plus 1, clearly, because you're incrementing K from P to R. So the current value would be K1 plus 1. What would be the new value of I1? I1 plus 1. And what would be the new value of J1? J1 plus 1. Okay. So we're going along with the flow. Does it always work? Yeah. Sorry. Yeah. So that that doesn't always work. So both of these perhaps are not completely accurate. So can you suggest new values? How would you do that? You could have your own technique for doing it, but let's come up with some suggestions. What would you give values for the new values of I1 and J1? Does it have to be I1 plus 1? Does it have to be J1 plus 1? Clearly, both of them are not going to be true. So we don't really know which particular loop will be, which case it's going to be. So in such cases, I would suggest just giving it a new variable name. Okay, so I2 and J2, because we don't really know what I2 is, and we don't really, but we do know that it may or may not be the same as I1, and J2 may or may not be the same as J1. Okay, so let's assign it new variable names, temporary names. Okay, so once we've done that, now we're proceeding forward. So what else? How do we do the maintenance? Any further suggestions? Now, can you in fact prove each one of these statements? Okay, so let's look at the first clause of the loop invariant. Okay, so can somebody sort of explain, will that be true? So we've given it, so these are in the previous loop. And in the current, so these are the current values. Current loop. Sorry, my handwriting is really terrible. So any thoughts on how you would actually do the first part, which is being able to prove the first clause, which is basically saying that the subarray AP through K minus 1 contains the K minus P smallest elements. Now, what are we trying to prove? So I generally say use the nomenclature to show that, okay? So first of all, we need to say, well, what do we know from the loop invariant and what do we need to prove? Okay, so before we get to this, we need to say, well, what do we know from the loop invariant? Okay, what is the loop invariant saying? Can somebody spell it out? Yeah. Yes, the lady with hard name. Okay. Yeah, so let's do it one at a time. So first of all, we're going to say what do we know, okay? So what is the loop invariant is telling us? And then the second part is what we have to prove, all right? So can you just repeat that? So can you say that in two separate statements? So what do we know? Okay. Okay, exactly. So we already know this. Okay, why is that? Because K1 was the previous values, K1, I1, and J1, and we know that from the loop invariant, it clearly states that this is already sorted, and these are, the smallest values, and they have not been copied. So now, what do we need to prove to show that? What do we need to prove? Yeah. Yeah. Okay. So yeah, exactly. So you got the variables correct because you're saying P through K1. Okay, because now in the current loop, K1 has been incremented, and we're saying K1 plus 1 minus 1 has to be in sorted order. So that's right. And we're basically saying that these two have to satisfy this particular condition. Okay, so this is what we have to prove. Now let's try to actually prove that. So the last part, proof. Can somebody prove, either part, just proving this part, for example? Kind of trivial, but yeah, go ahead. Yeah. Okay, yeah. So yeah, perhaps you did more than the proof, but yes, within what you said was sufficient amount of information to be able to prove this part. Okay, great. And what about these two? How do we prove that? Somebody else? Yes. Okay. Yeah, okay, let's do one of them. The first one. Okay, very good. So that's essentially completely accurate. So hopefully everybody is following this thought process. All right. So that's essentially what we need to do. And if I just show this to you, this is exactly what all of you have just suggested, that we've assigned different values of k, k1, i1, k1. In the previous loop, these are the new values. And by the loop induction, we're saying that we already know these following two facts, that that up till k1 minus 1 has the smallest elements of LNR in sorted order, and now and that these are given. Both of these statements are known, and we need to prove this. And now we're essentially saying that by going forward, line 13 is essentially, and we're taking the two cases separately, as you just suggested. So first we're doing the case where Li is less than or equal to Rj, and the second case can be done similarly. So you don't necessarily in all cases have to show the entire thing. So if this comes in an exam or something, you can, if it's fairly similar, you can just say, well, similarly for the reverse condition. Okay. So in this case, we're saying essentially this is the proof, and the proof is saying that line 13 is essentially in previous loop results in a k1 getting the next smallest element, and essentially that proves the first part. Okay. And the line 13 and line 14 in exactly what you've just said proves the second part. Okay, so you can just read through that, and essentially what people have just expressed, and that's sort of an example of how a loop invariant would be proven. Okay, for the maintenance part. Now the last part, which is the termination. Okay, and in termination, if you go back to the previous slide, but I don't think that's necessary, but essentially termination in this particular case is fairly simple. Okay, because number one, we need to say, well, is it going to terminate? And number two, when it does terminate, it gives us something useful. Okay. So can somebody do the first part? The fact that it does terminate. How can we prove that? Yeah. 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 So as long as this is those bounds are making sense, and you're not doing something funny with k inside, that's going to work. Okay. And so it's going to terminate. And secondly, how do we prove that it gives us something useful? Yes, David. Yeah. Yeah. Okay. So and essentially that's the entire proof. That's what we wanted to do, is we wanted to say that a P through R is sorted. So essentially, this is exactly what you've said, is that line 11 ensures that the loop terminates. Our termination case is equal to R plus 1. By the loop induction, we've just proven that a P through R contains the R plus 1 minus Pth smallest elements of LNR in sorted order. Okay, so essentially we're done. This part can be sort of a side point that you do have some additional elements over here, which are side elements called sentiments. Okay, so hopefully that whole process gives you an idea of how to write loop invariants. how to come up with a loop invariant, how to go through the formal proof. Okay. All right. So moving right along, let's now do an analysis, okay, of this algorithm, and let's try to see how can we actually quantify the analysis and see how much time it's going to take. Okay, the order of magnitude, the big O, the big theta, big omega values. All right, so let's start by defining T of n to be the running time of this algorithm. And now we need to be able to say, well, how can we actually determine what T of n is? Okay, now this is a divide and conquer. So you won't necessarily express a final equation, but because it's recursive, you might come up with a recursive equation. Okay, and hopefully we can solve that recursive equation at the end of it, and we can come up with a formal expression for the running time. Okay, so let's take a look at the first part. Now, initially we divide. Okay, that is this particular statement, and then we conquer, and then we combine. Okay, so can people suggest what would be the three, what would be the expressions for each one of these? So how, if I want to express T of n in terms of one of our big omega, big theta, or big O notations, could somebody give me an idea what T of n should be? Will it depend on n, which is essentially the size of the entire array, okay, p minus r minus p plus 1. Okay. So would it depend on that, the division? In division, remember, all we're doing is the first statement. It's line number 2. Yes. Yeah. So a big O of 1. But people agree to that? Big O of 1. Yes. Log base 2 of n. Okay. So that's another suggestion. So first suggestion, second suggestion. Any other suggestions? So remember, all we're doing over here is we have the values p and r. Okay. So p and r are integers which are actually given as an input, as input arguments to this particular function. Okay. So you're sort of going a little bit, you're thinking too much into it. We're not really, all we're doing is just look at that statement. What exactly is it doing? Is it doing something fancy? Is it doing something simple? This particular statement over here, line 2. Okay. So it's saying Q is equal to P plus R divided by 2, and we're taking the floor of that. Okay. So should the amount of time that it takes, should it depend on n? If n is 100 or a million, would the time vary? If you're taking 2 integers, dividing them by 2, taking the floor, would it depend on the number of, the size of the array? So any thoughts? I thought this would be easy. Yeah, it'll be what? It'll be constant. Okay. So big O of n, is everybody agree to that? Anybody who disagrees? So I spent a lot of time explaining big O, right? Okay. Okay, yeah. So now that's interesting. And your name again is? Davis? Okay, great. So Davis is suggesting it should be big theta of 1. All right. Any thoughts on that? All right. So clearly, big O is not a good answer. Why? Because big O is just an upper bound. The set of functions in big O could be order of n to the million. Right? That would still be part of the big O. So we don't. So when we know something is constant for all cases, then you have to be as accurate as possible. Okay, so we're not going to use big O. If we know theta, if that's big theta of 1, then we should express that. And if we're confused, then if you don't know, then we can use big O. But it's definitely, this is definitely a better answer. Okay, what about conquer? So what would be the amount of time taken for conquering? So essentially what we're saying is that these two parts are doing the conquering. So we now doing a recursive call to ourselves, but now instead of going from P to R, we actually going from P to Q, which is half the array. And then we doing another recursive call, which is going to the other half. Okay. So how would you express T of n? How would you express T of n? Think of recursion. All right. So can you give a recursive equation for that? So we already assume that we know what T of n is. Okay. And now what we're saying is that it's going to be it's going to take up the same amount of time as merge sort is, except that now the array is half in size. So what should be T of n? Yes. Okay, very good. So that seems to make sense. So 2 times T of n upon 2. Why is that? Because now essentially what you've done is you're doing a recursive call. If we know that this merge sort with n elements in the array is going to take T of n time, then clearly if you are calling merge sort with half the size of the array, then it's going to take n upon 2. Okay, we don't know what that is yet, but at least we have divided up the problem into a smaller problem, and hopefully at some point we will get a solution. And why is it 2? That's because you are calling it twice. Okay, so hopefully that's clear. Is there so the conquer is done. Now what about combine? How much time is the combining take? So now we calling another program, another function, and do we know how long that's going to take? Well, perhaps not on this page because we haven't seen that. Okay, so let's take a look. Theta of 1, T 2 times T of n upon 2, and now merging n elements we don't really know. Okay, so what we could do is just call it f of n. No, we need to determine what this is, and if you express this recurrence, what is this equation? What you could say, well, for n greater than 1, we don't really know, but we know the answer for n is equal to 1. As the problem becomes smaller and smaller, do we know the final answer? So if you're just giving an array of size 1, do you know what the amount of running time is going to be? It's going to be constant, right? So it's going to take some amount of time, and it's going to be a constant. So the way we can express it is that the constant amount of time is going to be theta of 1, the big theta of 1, and the recurrence relation is 2 times T upon n upon 2 plus some function f of n, which is the amount of time that the combination takes, which we don't know yet. Okay, so now we need to take a look at the merge program to be able to figure that out. Okay, so let's take a look at the merge program. And now we need to take a look at the entire merge program and to be able to figure out what is f of n. Okay, so if n is the size of this array A, okay, that we need to merge. In other words, we're giving it 2 smaller arrays, n upon 2, n upon 2, and these two together have to be converted into a single array, which is going to be of size n. Then how long is this going to take? Okay, so what we could do is, again, sort of a divided, so-called quote-unquote divide and conquer. We'll take a look at, no, that's a misuse of the term. So we'll just look at different parts of this program and see, can we analyze it? Okay, so the initial parts, how long are those going to take? So initially, it's just assigning variables. Okay, that should be fairly obvious by now that those are going to take constant times. Okay, that don't depend on n at all. What about this? So we're going through a loop from 1 through n1. Okay, and we're doing essentially copying the small the big array into small temporary arrays. So can somebody give me an expression for each one of these? Yes. Okay. So I'm looking for an asymptotic notation. Can you express the same thing in asymptotic notation? Okay. Sorry? Theta of n. Big theta of n. All right. Big theta of n. People agree to that, right? Because we disregard constants and we can just express that as big theta of n. Okay, everybody's agreed. What about the rest of it? So everything else, which is sort of constant, things which are theta of n, we can almost ignore them because this the entire running time is going to be dominated by the highest power of n. So far we've got the highest power of n is theta of n. Okay. What about this part, this particular loop? How much time is that going to take? Any thoughts? So we're going from k is equal to p to r. So it's just like a for loop. And remember that p through r is essentially r minus p plus 1 is equal to n. So essentially, those are the number of elements in that array. Okay. So how long should this entire loop take in asymptotic notation? Yes. Okay. So big theta of n. Anybody agree? People agree or disagree? Right. Yeah, so that should be theta of n. Why is that? Because essentially we're going through a loop, okay? And all we're doing is we don't have a sub loop inside it, okay? We simply have constant. We do have an if condition, and then we have two things which will take constant amount of times. So essentially, this entire loop is going to be the number of iterations is going to be a big theta of n. Okay. So all in all, what's the asymptotic notation for the amount of time that f of n takes? Theta of n, right? So three thetas combined together are still big theta. Okay. So this is what we have. And so now our recurrence equation becomes T of n is equal to theta of 1, and T of n when n is greater than 1 becomes 2 times T smaller versions of n, of T, and theta of n over here as well. Okay, because that is the amount of time taken to combine. Yes. Yes, yes. So, upper bounds and lower bounds are not very useful. If you can express something as theta, which is a tight notation, then you should always do that. Yeah, very important. Well said. Okay. So let's go. Yeah. Sorry. To big theta of n. So you're saying that just by looking at it, your intuition is that this should come out to be big theta of n. Makes a lot of sense, perhaps. Okay. I'm really bad at names, so you'll have to sometimes remind me repeatedly your names. Just once again. Sorry? Yuvraj. Okay. So Yuvraj's suggestion is that just by looking at this from intuition, you can tell that this is going to be theta of n. All right. So do people agree with that? Just let your intuition come out. Does that? How many people agree with this intuitive thought that it should be big theta of n? And people who don't have a clue don't have to raise their hands, but that's fine. Okay. So and how many of you think that is there something fishy going on? I'm not quite sure. All right. So some people think that it's not quite so obvious. So some people think, why do you think it's not so obvious? And somebody else can answer. Yes, please. Yeah. So you have to speak up. Sorry. My hearing isn't perfect. So what you're saying is it's got to be repetition. Okay, but what did you say after that? Yeah. So what do you think? It should actually be smaller than theta of n? So is it going to be the same or larger or smaller? I'm not sure if I heard you right. Do you understand my concern, my question? So I'm trying to sort of, I agree with what you're saying, that it's going to become smaller and smaller. But at the end of it, when you have those summations, is that total at the end result, is that going to be theta of n, or is it going to be bigger than theta of n? Is it going to be smaller? Big of theta of n. Why is that? Because you're essentially saying that it's going to be a whole bunch of them, but is that bunch going to depend on n, or is that going to be constant? Is going to be the number of elements that you have to add together. Are those going to be, is that going to be constant, or is that dependent also on n? That's also a function of n. So Yuvraj, you see the issue that's been pointed out, that just because you have a whole bunch of theta. So in the previous case, we said, well, there are three thetas, and just because there are three which are countable, then the sum of those three is still going to be theta, right? But if you had a number of combinations and that itself dependent on n, then perhaps the answer is not so obvious yet. Yes. Yes. Okay. Okay, interesting. So big theta n log n. So that's a revised suggestion. Okay. Anybody else have any thoughts on this? And a lot of times your intuition actually is right. Okay. So sometimes it doesn't work, but sometimes it does. If you've done enough of these, perhaps you can figure it out. So what are the formal methods of solving recurrences? Okay, so there's certain extent to which you can do, you can do it based on intuition, but you obviously clearly need to have some formal methods. Okay, so let's take a look at a few formal methods. There are three of them, which I listed out earlier. The first method is called a recursion tree method. Well, it's not first or second, but it's just one of them. Another method is called, induction again comes in. Induction is one of the favorite methods to prove things for mathematicians. And then there is, sort of a shortcut method. Okay. And so let's take a look at each one of these. So this is the recursion tree. And the recursion tree essentially is fairly obvious if you look at it. We're basically saying that if you look at this recurrence equation or recurrence relation, then you're essentially saying that if you have n, for some value of n, you can say, well, we know how much time it's going to take to do part of it, which is the cost of divide and merge. Okay. So dividing and merging, we know is going to take a certain amount of time. And then it's being divided up into two smaller problems. And each one of those are going to take a certain amount of time. Okay. So if we look at what we've already been able to see, is that the cost of divide and merge is going to be constant. Okay, that's going to come out of here. And the cost of sorting the smaller problems are going to come out from here. So this 2t upon n upon 2 is essentially can be represented as a recursive tree. Okay. So now we can keep on taking this forward. So let's take a look at the next stage. So we know C of n, okay? Now, what would be the cost of divide and merge at the layer below it? Okay. How much would that be? Any thoughts? So we already know this is going to be C of Cn. So if you have divided up into two smaller parts, just take a look at one smaller part. How much time is it going to take to divide and merge that half of that? Half of Cn? How long should that take? Just the divide and merge part. Yes. That should also take, no, I'm just looking at one part. Okay, so now okay, so this should be Cn upon 2, and this should also be Cn upon 2. All right, yeah. You could do that, but let's not do that, because that's sort of jumping ahead. And but you could do that. You could do it in either one, and both of them would actually give you the answer, right? Okay, but let's just keep it simple, and let's say that it's going to be Cn upon 2. Okay, because theta of the problem with that thought is that if you express this as theta of n, it's not giving you you won't be able to solve the problem using that approach. Okay, because essentially what we're saying is we're dividing it up into two smaller problems, and that's not being captured in the theta. Okay, it's that part is not being captured. Okay, so this is not going to lead us. What about the last part? So at the bottom, do we know what that is? That's the cost of sorting the sub problem. So if you take a look at any one of them, what is it going to be? What is that going to be? Yeah. So it's going to be C upon n upon 4. All right. Will people agree to that? Yes. Okay. So it should be T of n upon 4. Okay. So we have two thoughts. T of n upon 4 or Cn upon 4. Which one should it be? The cost of sorting the subproblem. Okay, so now there's a difference in the term. So this is the cost of divide and merge, and this is the cost of sorting. There's a difference. Okay, some of it we know, some of it we don't know. So over here, if you look at this, we know what this cost is going to be, but we don't really know what this is going to be. We're just expressing it as a term which is expressing how it could be. Okay, so which one of these is making more sense? T, right? So it should be T upon n upon 4, because we haven't really solved that problem. And the problem is much more than just the cost of divide and merge. If I just said the divide and merge portion, then that would be right. Okay, but since I'm saying the cost of sorting the entire subproblem, that comprises of more than just divide and merge, and so it's actually going to be Tn upon 4. Okay, so you can see where we're heading. Now you might say, well, this is great, but what happens at the end? I mean, this is going to keep on going forever, right? Is it going to go on forever? Well, no, yeah. So because you're dividing it up into smaller and smaller parts, so eventually it has to come down to a single digit, right? So eventually n upon n is going to become, and if you disregard, the fact that n could be a power of 2, and let's just disregard those cases, but let's assume that n is a power of 2, then essentially this is what we're going to get. Okay, so eventually you're going to get down to a constant. Okay, so to be able to sort a single constant, which is what we already have seen, that takes a constant amount of time. Okay, that does not depend on n. Eventually it's going to get down to something which does not depend upon n. And now we're going to do a total computation. Okay, so we're going to do a very simple computation. Perhaps this is going to answer the question that could we have used theta. And you can see that theta would not have been very useful, because now what we're saying is that this particular layer, if you sum up, then it's simply going to be total of Cn. But if you look at this particular layer, okay, there are two sub problems, and those two added together are going to take Cn. Okay, and here there are 4 smaller problems of merge and divide. And those are each going to be taking Cn over 4, and so multiplied by 4, that comes out to be Cn as well. Okay, so each of these layers is still going to take the same amount of time in terms of n, some constant, times n. Okay, and so what is the total going to be? Somebody else. Somebody else. Yes. log base 2 of n times Cn. Okay. Yeah. And so, Yuvraj, your initial intuition was somewhat right. Basically, you have, and by the way, every time we're going to write LG, it's going to be assuming that it's log to the base 2. Okay, so it's shorthand notation. So, or for that matter, we could use different log as well, but if you want to express it as asymptotic notation. But now you can see that the height of this tree is actually something which depends on n. Okay, and the fact that this height depends on n, that's why you can't just say that if this was constant, for example, this was 3, then we could have actually neglected log of n. Okay, but since this height actually depends, is a function of n, and that's why you need to take Cn, all of these terms, and you need to multiply it by the height. Okay, so the height is log of n, so it becomes Cn log of n. And you can add another Cn, but that's not really critical. Okay, so so essentially, we've been able to show that that you can express this as a as an expression, and you can actually express this now that you've learned big O, big thetas, and so on. You can express that this is going to be theta of n log n. Yes, question. At the end, that's sort of looking at the end cases. So if the actual number could be log of n, or it could be log of n plus 1. Those cases are, and it's not really important, because if you're looking at the asymptotic notation, I wouldn't want to waste time trying to figure this out. Okay, because it's a smaller power of n. So when you're looking at asymptotic notations, that drops out. Okay. So essentially, it comes out to be theta of n log n. All right. Okay, so that's great. We've been able to use one technique and to be able to, so as I said, there are 3 techniques. We've been able to see how the recursion tree method can solve this problem. Okay. Now let's take a look at a slightly more rigorous method, which is referred to as the substitution method. Okay. So the substitution method, also I would like to prefer to call it the induction method, but it's generally referred to as a substitution method. The idea, as you might imagine, is that you guess a solution, as you always do whenever you use induction, the mathematical induction technique, and then you use the mathematical induction, go one step forward, and to show you make a induction hypothesis, and then you try to show that you can prove that the hypothesis. Okay. The reason why computer scientists are calling this is substitute is following. I think sometimes we try to invent new terms. Okay, so let's take a look at the following example. All right, so this is essentially the same example that we were looking at earlier. Okay, so here we had theta of n, big theta of n, and we have expressed big theta of n as C of Cn for simplicity. Look at this example. We could have just had theta of n, but I'm trying to simplify it in the first example. Okay, so I'm saying that let's assume I'm giving you a recurrence equation, and the recurrence equation has the following form: Tn when n is equal to 1 is 1, and when n is greater than 1 is 2 times Tn upon 2 times Cn. Okay, and we're going to assume that C is non-zero and it's not negative, okay, as in the past example. So I'm going to start off with hypothesis, which I don't know if it's right or wrong. It's just a hypothesis. Okay, so let's come up with the hypothesis that, as perhaps Yuvraj originally suggested, is that it's big O of n. All right, so I'm not taking theta of n right now because that requires proving upper and lower bounds. So I'm just going to take big O of n. So if you can do big O of n, maybe we can do big omega of n, and we can do theta of n. Okay, let's do it in step by step. So let's assume that this is big O of n, and by the induction process, we'll be able to either prove it correct or incorrect. Okay, and our guess is that it's going to be proven incorrect, right? Because we already know it's actually n log n. It's not n. Okay. So when we say that T of n is big O of n, first of all, we have to express this as an equation. So we know that the formal definition of this is that it implies that T of n is less than or equal to some C times n for C greater than 0, okay, for all n greater than n naught. Now, we've got two C's, and it's important to pay attention to the details when you're doing induction, is that these two C's don't have to be the same. Okay, so I'm going to call this C1, and I'm going to call this separate from C. Okay, so this is C1 and C to differentiate between the two. So we're saying that this is the guess. Okay, so now for people who have done induction before, how do we start with induction? So I'm sure you've done induction in one of the discrete math courses. Yes, the general there in the corner. Sorry, you have a base case. Okay, so you come up with a base case. And what could be the base case? Okay, so we basically try to say that the first case we come up with when n is equal to 1. Okay, and we try to say, well, is that true or not? Okay, so is the first case true? Well, let's take a look. So if n is equal to 1, we already know that T of n is equal to 1. This is already known to us. Our hypothesis says that it has to be less than or equal to C1 times n, okay? And so this comes up to is 1 less than or equal to C1, okay? So I can say yes, because C1 could be any value, right? So as long as C1 is greater than or equal to 1, as long as C1 is greater than or equal to 1, this condition is true, okay? So we're fine so far. So the base case has been established, now the hypothesis. Okay, so what should be our hypothesis? So we've already got a guess, but the guess is not necessarily just the hypothesis is a little different from the guess. Okay, so guess is the ultimate solution. Okay, but the hypothesis has to be conducted in two parts. Okay, we're going to take a small part, we're going to assume that something is true for some part, and then we're going to use we're going to go through a process to be able to say that, well, then it should be true for a bigger part. Okay, so can you come up with an induction hypothesis based on this guess? And this is a lot of times this is not done correctly, and so you need to pay. It's not trivial. It's fairly straightforward once you've done a few of these, but is sometimes people get confused with this, okay, and you can make lots of mistakes. So the gentleman in the back, yeah. For some n, yeah. Where's the R coming in from? So say that again. So Tn plus 1 is less than or equal to C1 times. Okay. For all n greater than or equal to n naught. Okay. So yeah, seems to make sense. Any corrections, suggestions? Does the n not have to be true in the base state? Yeah, so in the base case, so in this case, what is n not? For essentially for greater than equal. Well, one of the conditions is that n has to be greater than 0. So we can say that n naught is actually equal to 1 in this case. Okay, n greater, this is going to be trivially true for n greater than or equal to n naught, which is 1. Does that make sense? Well, so that's so n actually is equal to 1 in this case. So you can't really put this in yet. Yes, they have to be. So let's take a look at all the cases, and then eventually what we need to decide is that what should be the value of n naught to satisfy all the cases. Okay, does that make sense? So in this case, sort of n naught is not really relevant because n is fixed. Okay, and as you go forward, then if you have multiple situations where n naughts have different values, then we will have to make sure that we pick the largest value of n naught. Okay, as we did in one of the earlier cases. So, so the induction hypothesis, gentlemen suggested this is reasonably accurate. I'm going to express it slightly differently. And again, this is where that small trick that I said comes in, because I'm going to use a different value of n. Okay, just to make it simpler, but you could do it this way as well. But because as you go through this proof, it comes in handy to use a different variable. Okay. So I'm going to use a different variable, and I'm going to use m. Okay, so I'm going to say for all m less than n. I could have said it differently, but I'm saying for all m less than n, let's assume that Tm is less than or equal to C1 of m. Okay, so this is pretty much what you had said. Okay. So it's sort of similar, but I'm using a change of variable, and I'm saying, let's assume that this is true for all values of m less than n. And now what we're essentially trying to prove, well, the hypothesis is that if this is the case, then we need to prove that T of n, right, is also less than or equal to C1 of n, C1 times n. Okay, so you notice that now we've gone from proving that if you have a range of n, so we've taken, let's say, all values if n is over here. Okay, so m was up till here. This is the range of values for which the hypothesis is true, and we're saying if it is true for this range, then it's also true for the value of n. Okay. So now that we've clearly stated our hypothesis, we need to prove this.